This tutorial is on Cotter joints. So what is a Cotter joint? The Cotter joint is a temporary fastening used to connect two coaxial rods which are either in tension or compressive forces. So you can see there are two rods which are either tension. So here it is both in tensile force, and Cotter joint is to connect this one. An example, it can be seen that this is this is first rod and this is the second rod which are connected, and maybe it is applied to tensile force. So this is a Cotter joint. So what is a Cotter joint? It's a flatward shaped piece of rectangle. So it is a flatward piece of rectangle cross section, and which is tapered either in one side or both sides from one end to another. So usually we say that is 1 in 24. So 1 in 24 means if you move 1 units here, you have to move 24 units here. So totally, so this is we say 1, then this is 24, and there is theta in this one. So this tapering is called this 1 in 24 tapering, that is used in the Cotter joint. This is just to make the fit, perfect fit, when we use this Cotter joint inserting into the hole. You can see that is inserted. So how it affects is like this tapering happens. This triangle can be drawn here in this direction. So what happens is that when the thickness is increased, so on one side it will be flat like this way. One side it will be flat like this way, and this is increased. Now tapering is applied at this point. So you can see when you extrude this part, this type of tapering goes on here. So that way it is happening. I hope in this direction. In this case, it is applied in this direction, and maybe we applied here, and a taper is formed at this direction. Given some thickness here, then it is tapered. So a tapering will be going like this way. And what are the application? It is widely used to connect the piston rod and cross head of reciprocating steam engine. So that is a piston rod and engine as a joint between piston rod and tailor pump, foundation bolt, strap, end of connecting rod, etc. So the major idea is like it will be used for connecting the piston head and the rod of the engine. So these are some of the failures that happens in this Cotter joint. So Cotter joint will have three parts majorly, and it can be seen here, already discussed here. That is, the first one is socket end. So this is like a socket. Then there is another called spigot end. The spigot end will be entered into the socket. Now once entered, there is two holes that are aligned. On that one, the Cotter will be entering, and as a result, once this entering, it will be fastened. So the final shape you can see here, that is Cotter is entered here. There is this is the socket part, and spigot is inside this one. This part is spigot, which is entered into this one. And in fact, this is not spigot. Inside that one, spigot comes. Spigot's the rod. This part rod is shown here. Then when come to the some failures of this one, the first part is this is the failure of the socket rod. At the end of the socket there is a small rod, and the failure happens when there is some tensile force happening. That this is explained, or some equations you can find in the data book 4.17e, page number 67. And this, the second case is like that one. This happens, the fracture or the crushing that happens to the socket part at the point of Cotter end or Cotter's hole. There is a Cotter hole here. Here there is a Cotter hole, and the failure happens at this point. Now the third case is this is the failure that happens to the spigot. So the inside there is a spigot, and Cotter passes through the spigot, and because of there is a hole. There is a hole here. This happens here. And next one is about this is happens to the failure happens to Cotter itself. Cotter might be sharing and crushing, and it will be cut into three pieces. And this one happens because the Cotter is placed at this point, and At this point, when tensile force acting, the cotter will try to push here and two pieces will be failing like this way. And some of the advantages of cotter joint are it is simple to design and manufacture and can be easily assembled and dismantled with ease, because you can just remove the cotter from that hole. Very high tightening force due to wedge action. So as a wedge action, in fact, that is a tapered action. So as we know, there is a tapered action. It's because tightening force is much high, like when we hit or over this one, it is more tightened, which prevents losing of parts in service. Then the major force acting here is the friction force, obviously, because of the wedge action here. And types of cotter joint. Following are the common used cotter joints. That is, first one is socket and spigot cotter joint, then sleeve and cotter joint, gib and cotter joint. So majorly we are focusing on socket and spigot cotter joint as per KTU syllabus. Okay, now socket and spigot cotter joint. So this is the same cotter joint as I have shown here. This is the cut diagram of this one, or section diagram, out of which you can see first part is the socket. Socket means this part from here. It's like socket starts from here to here. So spigot is inside this one. So this comes the socket part, and this is shown as a socket here. And this one is the cotter. Basically, this is the cotter. And finally, there is a spigot, the rod, and we can see only the rod, and the whole other is inside. This one is as the cut section. You can see this is the spigot. Now there are some assumptions for stress analysis of cotter joint. The rods are subjected to axial tensile forces. Means there should be both rods. Rods means there is one rod here and another rod here. So these rods are subjected to axial force. The effect of stress concentration due to holes is neglected, because there is some holes here, that is we are neglecting the stress concentration. Force is uniformly distributed in different parts. So uniformly distribution is there as there is no stress concentration. So these are assumptions. And now we come to the design procedure of cotter joints. So you can see the figure already here. This figure we can find out in the data book itself, that is in page number 66, figure number 4.4, that is data book handbook. You can see the figure. This is quite slightly different figure, it's same, but however the notations and the parameters used are same there. And how to design this cotter joint? There are two methods to design the cotter joint, in fact. So the first method, like these are the parameters. The major thing is that first we will find out the D, that is the diameter of the solid rod. Then from the solid rod's diameter, all other things have been calculated based on this one. So you can see D1, which is we can see this D1, it is found out, and D1 is related to D, so 1.25 D. So in fact D, this is the actually spigot diameter, this is crushing area diameter, the second part. So let that be done. So D1 equal to 1.25 D. Then thickness of the cotter, thickness of the cotter, that is related to this D1. Now D1, once D1 is found, we can calculate the thickness. Then width of the cotter, that is B is equal to B, that is equal to 5 into T. So we say like B, the width of the cotter B is equal to 5 into T. Then diameter of the socket, obviously the socket is having a diameter which is represented as capital D. So the socket is a maximum diameter is this one in the socket, that is equal to 2 into D, which is represented in terms of the solid rod of the spigot. Then it comes the diameter of the collar. So diameter of the collar is given as D2 is equal to 1.5 into D. So we call this as the, again this is a part of a spigot and is given as D2. And then it comes the length L1 is equal to 0.75 D and L is equal to 1.25 D. So we can see that it's representing an L1 here, that is the end after cotter of the spigot, L1. So L1 just represent what is the length of the cotter, a spigot, when once entered into the cotter. And L is, we can see the balance part of the spigot. We can consider as a balance part of spigot, or maybe a common length of this one is socket as well. Okay. Now it's come to thickness of the collar. Thickness of the collar T1 is given as 0.5 D. So you can see this is the collar which in spigot is entered into this socket. So you can see this part is spigot is this part. So this part is spigot. So because it entered into this one, its thickness is T1, is 0.5 D. And thickness of the socket, now the thickness of the socket is given as T2. That is, here you can see the T2, that is equal to thickness of the cotter, thickness of the socket end. So here there is some end. After this one, once there is a small clearance, there will be some thickness that is equal to 0.5 D. And length of the cotter, that is L is equal to 4 D. Now cotter total length is assumed to be 4 times the diameter of the spigot end. And clearance C is equal to, that is, we have a clearance here that is equal to 3 mm, or it can also be the clearance here that is equal to 3 mm. Now that is the method, like all the parameters we are finding out, and don't worry, this is available there in your data book, what are the parameters. Now there is another method, like through equations we can find out that is, first the resistance of the cotter and rod end to crushing. So this is like the cotter, how much resistance. First we will finding in this method, first we will go for this equation P equal to pi d square by 4 into sigma t. From this diameter is found out D. Then further we will just move on to other equations like resistance of cotter and rod end to crushing. So once we know the diameter, we can find out the P. If not, P can be replaced with the terms of D, and we can find out this equation. And next, second one, tearing resistance of the rod. And what we are trying to do is, like, we will follow this one, all the equation, we will be finding all the equations for design of the rod, then we will be finding all the equation for design of the socket, and finally design of the cotter. So with this we will be designing our cotter joint. Thank you.